This is Paul Van Huffel with Altair Engineering. I'm a Senior Applications Engineer with the Global Technical Support Team. And we're going to talk a little bit about strategic use of analysis tools. Just very briefly, we're going to rehash over this stuff because we covered some of this, at least a good discussion of it before. I added a few extra slides just to kind of illustrate. And then we're going to jump into defects from injection molding coming from filling and defects coming from packing. And then a few examples in the software of where you might see some of these things in the results, and kind of see how some of these things are captured in the software. So let's dive in. So once again, this is our sort of our manufacturing analysis process. We think about the things that we need. What is it that I'm trying to simulate? What's the objective? What are the answers that I need to get? By understanding what it is that I'm trying to seek, I can understand what physics I'm trying to simulate. From there, then I can delve into things like material properties, loading conditions, constraints. Essentially, it's the same idea as the free body diagram, just extended. So, all simulation, regardless of what you're trying to simulate, all simulation, all analysis of this type should have these kinds of considerations listed. It should always start with your objective, because from your objective, you dive into the model. What's the physics I'm trying to represent, and therefore, what do I need in my model so that I'm not overdoing it for the answers I'm trying to seek? So, preliminary analyses, right? These are done very much up front. Material selection, gate location for injection molding, because we're going to focus this on injection molding. Process window analysis, so my fill time, my mold temperature, my melt temperature. What are my ideal conditions, and what are my reasonable conditions for it? Not just what's the perfect conditions, but I want a process window that I could run a truck through, not not fall off a cliff from. So anyway, and so you want simplified models and things for that. You want reduced models to determine things like your process window, because you're going to do lots of little runs to get pressure to fill, clamp force, temperature rise from shear rate, and the shear rate limit that what's the maximum shear rate that you encountered in that path during that filling process. And then you look at things like cooling time estimation, looking at, say, the thickest section of a part, and there are hand calcs for that, and there are simplified tools for that. And depending on where you're at, are you estimating, or are you doing something a little bit more involved? Are we getting just a little farther along than merely estimating, or is this a kicked off project, right? In which case, that's going to guide some of those decisions. Intermediate analysis. Now we're starting to look at, let's look at not just where to put a gate, but let's look at, some of that gate and runner design optimization. Let's look at what are good sizes for these things. Let's look at some detailed packing analysis. When is my gate seal specifically, so that I can really kind of define what that process is going to be at the press. Next, obvious molding defects, right? When I'm running the simulation, I'm looking for things like, geez, this thing's going to take so much pressure to fill. I don't think I got enough in my press, right? Depending upon the screw intensification ratio, if you have a screw that only has a 3-to-1 intensification ratio, and you only have 2,000 PSI, you only get 6,000 PSI plastic pressure. That's all you can get, right? So thinking in terms of the pressure that the plastic can get, the temperature of the melt itself, not the barrel, not the heaters, not the hot runner, not the water going into the mold, but we look at the melt temperature. We look at the cooling rate, not the temperature of the mold, but the rate at which the heat leaves the polymer into the mold to get it out. Because a mold is really little more than, aside from shaping, it's a heat exchanger. From an engineering perspective, a mold is little more than a heat exchanger, okay, thermally speaking. So think of it like a big radiator. I'm going to pump something that's hot in it, and I'm going to cool it down. Ta-da, heat in, heat out, and the rate at which it cools, and the fact that you want it evenly done across that geometry. That's easily said. Not always so easily done. Okay, fiber orientation, and things like that. So now you get a little bit more detailed information. Maybe you want a full model, right? Maybe you even have some basic or simple mold geometry involved in that analysis. Maybe you just put kind of a block around it so that you can kind of get that thermal transfer of the heat being pulled away from the cavity. So, and then of course, lastly, now we have the very detailed analysis, detailed cooling, baffles, inserts, bubblers, heat pipes, specialized, beryllium copper inserts or aluminum inserts, or maybe for the sake of wearability, you may be forced into using stainless steel, right, which actually conducts heat much less than the P20 steel that maybe the rest of your mold is made from. So it's good to get to understand not just the polymer materials that are involved in your simulation. Sometimes when you get to these more advanced, more detailed analyses, you got to get to know some of the tool materials that are made out of, that these molds are made from. P20 steel, 4140 steel, some grades of aluminum, H13S7 for a lot of fiber-filled materials because they can be hardened much harder and then the glass doesn't wear away the tool so fast. Beryllium copper, Ampco 940, Ampco 97, and other various materials, things like that. So, plus you might get into product structural analysis. Maybe you need to initialize the part with some information like, say, the fiber orientation tensor, in order to get a detailed structural analysis or performance analysis of that part. That becomes kind of an important thing to really do your analysis homework up front so that you're doing fewer simulations later. That's how we make ourselves cost effective as analysts. So just a couple extra slides to kind of illustrate what we're talking about, right? With preliminary analyses, we're talking about things like hand calcs. Here we see, simple hand calcs. We just rough it out. What's the pressure to get from my injection location? Call it an average thickness as we go through, or you can do it in segments and add them together. And then finally, and get a sum of the pressure drop. Next, you might look at simplified geometry. The images below are taken from a mold flow user group presentation paper that I sent to the European conference in 2004, I think, late 2004, where I did an example of simplified geometries so that I could do quicker runs because, the model on the right, that very simplified model, which you can see, the pressure to fill it is almost identical. It's only just a little higher in the simplified model than the real one. Pressure to fill is, of course, guided by the flow length. And the illustration here, it wasn't actually a half model. It was actually a whole model, but it was cut in half for the sake of speeding up the post-processing time. It was officially run with a full model. Anyway, but even compared against a half model, it still ran in like a 1/10 the time or something like that. I mean, it was like a 10x speed up. It was ridiculously fast. But I get almost exactly the same pressure to fill and clamp force because I have the same projected area, I have the same volume, the same nominal wall thickness, and the same flow length. Because I have those four things all the same, I get the same mathematical behavior. And the whole point of analysis is I need a model that behaves mathematically like the thing I'm trying to simulate. And that was the whole point of this paper, was to illustrate that sometimes we overdo it with our modeling and we're really kind of wasting time in too much modeling, too much meshing, if we're not looking at all those extreme details. If those big details, tiny little ribs and facets, if that's not part of what we're trying to simulate at that time, then that's too much. We've gone too far in modeling, and we've, that costs time. It costs time in compute resource. It costs time in modeling it. So being frugal with our time and our resources, because it doesn't matter, as time progresses, as the computers get faster, and then we send them bigger models. So there, we always catch up to the resources. Simplified models. So now we're getting down to things like coarse mesh, minimized boundary conditions. I still have my full, I'm still modeling this thing, but as you can see along the edges here, the element sizes are fairly big. But this is a solver that was, in our solution, we use the fast solver, and this solves, in much less time than trying to do a full simulation with 4, 5, or 6 layers of elements everywhere in this model. I get very similar results, and it does it much quicker. And so I can certainly identify things like the pressure, when I distinguish my melt temperature, my mold temperature, and my fill time. When I'm looking at those 3 things to develop my process window, this is a great way to do it because it runs a lot faster. I can look at that pressure to fill, and I can, fill from that. I can go into an Excel sheet and look across multiple iterations to kind of get an idea, like a DOE. Eventually, we'll probably package up some form of DOE, or you could probably even use hyperstudy. Well, that won't be an obvious thing to do right now, so I wouldn't even put that on anybody. I don't even know if I'd shove that at a graduate student. Anyway, so next, we use these the fast solver to get things like filling and cooling, because they just give us some preliminary information, and it gives us a little more detail, a little more, forgive the pun, color into what it is that's going on. So now, going to the other end of the spectrum, we start talking about correlating this to what we see at the machine, which is kind of the topic of what we're going to get into later. After this section, we're going to start talking about the actual defects. So we're talking about bridging this gap between the what we're doing in simulation and what you're seeing in reality. So, in understanding how we translate these things, there are things at the machine that, parameters, various qualities of the analysis or various qualities of the process and the equipment that are different at the machine than they are in simulation, simply because one of them is really doing it and the other one can simplify those things because it doesn't need them, right? Like cushion. Okay, so here we look at some information that I got from some plaques that were molded for Altair, so that we could compare things like CT scans of fiber orientation at various locations in the plaques. But we needed, if we're going to simulate it so that we can mimic the same thing, I got to have the same process, right? Otherwise, I don't have a basis to compare against, right? So, I've got, several, 10 plaques here that were molded. And then I've got the cycle time, the total cycle time, mold close to mold close, is about 30 seconds, right? 29.7, 29.8, 29.9. It's roughly 30 seconds. Fill time. Now, fill time in simulation means the time that it takes to fill the cavity completely. But we don't know when that happens inside an actual mold. What we do know is the fill time that it takes until you get to the transfer point. That's our fill time coming from the machine. So they mean different things depending on your context. So these are things we sort of need to be careful about our definitions when we start comparing an analysis to what was happening at the press. Cushion, shot size, decompression, right? I look at a total shot size, right? It says 3.99, but that's not actually the total model volume. That's actually more than the total volume because of cushion, right? Cushion is that little bit of material that's left in the barrel ahead of the screw when you get into the pack and hold phase at the machine, because if you don't have that, you can't consistently pack the material. You need a little extra in front of that screw to guarantee that you are in fact applying pressure throughout your cavity. If you don't have it, you're not transferring pressure and you have inconsistent part weight and other things. So at the machine, the total shot volume is the shot size minus the cushion. But then we also have to take into account that at the full shot position after decompression, like our 3.99 here is after decompression, right? So we have back pressure applied when we're turning the screw back, and then we decompress to get to the 3.99 that's sitting here, or 4 in the one case. This is without pressure. This is with nothing more than maybe 175 to 100 psi of back pressure while we're turning the screw. When I get to the transfer position, right, when I hit that transfer cutoff position here, I am at, I have a peak pressure in the barrel that is my transfer pressure, right? So I see injection pressure, yeah, hold pressure, decompression. So the injection pressure listed here is the pressure when you hit transfer. The hold pressure is the pressure that's applied when you're at the point of cushion. In the case of the transfer pressure, that's not a uniform pressure throughout the cavity to the end of the fill, because it's going to scale from that pressure to zero or near zero at the flow front. So I get kind of an average across that distance. Some of it's runner, some of it's part. And so how that affects your tonnage depends on where it is in that process, right? If I'm sprue gated into the part, it's going to affect my tonnage a little more greatly than if I have a long runner system. Please excuse the dog. Okay, so you'll get different effects on the tonnage. Okay, so in the spirit of having compression in this process, I took the tape parameters for this material and used them to get the density and account for the compression of the material at the different locations, so that essentially I'm accounting for my shot size not just as a volume but as a mass, as a shot mass, to represent the same mass that will be in my model in the end. In our simulation, we don't use the compression during filling, but we do in packing. During filling, we're using Stokes flow, and so we assume that the material is incompressible. So by doing this, I can account for what is my actual, what's my pressure at transfer is about, almost 43 megapascals. The average hold pressure puts me at about 23, almost 23, yeah, it's about 23 and a quarter megapascals as my average hold pressure. And that's plastic pressure, right? Because I have to convert through the screw intensification ratio, the 10.1, and the compressibility of the material in order to get to these values. It also affects, just so ever so slightly, my transfer position. It's not a great deal of difference, but it's a little bit. If I'm trying to be very fussy about comparing one thing to another, the analysis to what's going on at the press, then I want to be very particular, because a lot of little errors can eventually add up to something significant, and then we're left scratching our heads. Why are we not quite on it? So trying to account for as much of this as possible, so that eventually someday when we go to doing these things in a more automated way, we can have these things fully accounted for as a matter of method when we go to do this somewhere down the road in the future. So our end result. So here I'm looking at the results of a 9-layer mesh in my part, not just 5 or 6 or something like that. I went to 9 layers this time. I actually have some other runs lined up to do where I have 12 and 24 layers, because we had 24 layers of CT scan in the actual plaques. If you look very carefully at the little sketch down here, you'll see like little circles on the plaque. Those are basically slugs in the model, so that I can get the locations of where the CT scan was taken. That way I can compare fiber orientation results much in the same way as was done in the CT scan. So what I'm looking at in the graph here is the pressure to fill. And you see the transfer pressure over here with a couple of different runs. The blue is where I did not use pressure dependence. In one case, I have relaxed tolerance for my convergence. The other, I have tight tolerance for my convergence, the solid line here. I used relaxed tolerance for using it with pressure dependence, because I had to run that one on my laptop. And with tight tolerance, that takes a much, much longer time and takes a whole lot more memory. So I ran it with relaxed tolerance. But looking at the results of relaxed versus tight without pressure dependence, they're very much the same. I'm getting essentially the exact same answer without pressure dependence. What do I mean by pressure dependence? It is that in my viscosity, I have a term to include pressure dependence of viscosity when I calculate the pressure drop as I'm going into the part. So with pressure dependence, right? As my material compresses, it becomes a little more viscous. Kind of makes sense, right? These materials are at least mildly, if not greatly, compressible. A lot of amorphous materials like polycarbonates are more compressible. So things like pressure dependence may make a little difference. Here it's a very small difference between a little bit below, like 38, 39 megapascals and just over 40 megapascals for with pressure dependence. So a couple of megapascals in this case. In other cases, I've seen it take 4%, 5%, even more. Some polycarbonates, significant percent difference. So again, that's part of my Antec paper. So if you are part of Society of Plastics Engineers and you attend the online conference and find my paper, and you'll see my presentation there regarding that and the fitting of Williams-Landau-Ferry coefficients. All right, so viscosity models, right? So we talk about viscosity and pressure drop. Viscosity for these polymers is not linear. It's not Newtonian, right? It does, when I change my shear rate, my viscosity changes. So as I'm increasing the speed of my flow incrementally, as I get faster, it takes less and less pressure to keep adding to the speed of the flow. It still it still does, it still takes more pressure. It still takes more force to get that to happen, but the incremental amount more is not linear, right? As I go faster and faster with water, I can just draw a line and say, okay, I want to know what the pressure drop is as I fill this thing at whatever speed. I got one viscosity, right? And so I just have, I have one viscosity, so the pressure is a linear extrapolation versus that flow speed. In this case, not linear. It kind of gets, it trails off and starts to look almost asymptotic. So something to keep in mind. And so pressure dependence factors into that zero shear rate viscosity. So when you're looking at a 0 T, that's our zero shear rate viscosity, and that is that's the thing that will be affected by both temperature and pressure if we do both temperature and pressure dependent. Temperature dependence is accounted for with Williams-Landau-Ferry equation for time temperature superposition. That does include a version that has the pressure dependence, and that's what I was doing in that other example. That's what part of what I was testing there. Okay, now we're going to get into some of the common defects from molding. And some of the things that we might see in simulation that go along with that. So we're going to talk a little bit about the defects themselves, and maybe jump back and forth, or just when I'm done with the slides, kind of go back over some of these things with some examples. So one of the most common is short shot, right? If I don't have if the flow length and the viscosity is so high and the flow length is so long that I just don't have it in the machine to be able to fill that cavity, I'm going to get a short shot. Or if I trap air and I just can't get the flow to go any further because I've not properly vented, I can get a short shot that way. There's a couple different ways short shots can emerge. Splay. Splay has all kinds of different sources, right? Splay could come from water in the mold. Splay could come from contamination. Somebody spraying a mold release or something in the sprue, and so the first couple shots maybe get some splay on them from the contamination. Maybe you have contamination in the material. Perhaps somebody was using anti-stat liquid on the polymer and put too much in it. So now you have maybe a volatile compound that works its way out. Or maybe it comes from shear, right? If it's coming from contamination, if it's coming from not drying the material, you're not going to see that in simulation. What you will see in a simulation, though, is a source of shear if you think you're seeing shear splay. Or if you think you might get shear splay from, say, turning a corner, we can look at the shear rates as we turn those corners and assess whether or not there's a reason for shear splay, right? I've had a case where we had splay in a part, and it wasn't, people kept saying it was shear splay, but there was no feature in the tool to create the shear in that region. There was, however, when we backed off and we did a series of short shots and worked it backward, what we found was actually there was trapped air. So there was a failure to vent, and what happened was the bubble ran along the edge of the part, and as it got near the flow front, the bubble got bigger because under high pressure, that air is well compressed, and as it runs along the edge and it gets to softer and softer skin in the material, all of a sudden the bubble gets bigger and bigger, and pretty soon it's inside the melt because it just bubbles its way into the melt along the edge of the tool. So when it did that, then it emerged at the surface because bubbles go to the point of least pressure. And so it bubbles up to the surface, and then you see splay on the surface of the part. And I think I even have a picture of that in here. That was a topic of my Antec paper in 2003, was the fact that you can get what we call adiabatic shear or adiabatic splay and blush in injection molded parts. So we get shiny spots, dull spots, and splay marks and other things that can happen in there. Knit lines. The line, I mean, there's the line itself, right? If you get it nice and clean, but if it's not so nice and clean, you could have a dull hue around it, or it could have a shiny hue around it because maybe you remelted some of the material along the edge, or maybe you got flow lines because you wrinkled some of the material from the gas trying to escape as the knit line was forming. Maybe you had a large trapped air, large amount of trapped air as the knit line started to form, and so the air trying to get out, it basically forms like a capillary between the two flow fronts, and the air is jetting through there. It gets very hot, and it can remelt the material. It can vapor hone the material, make it dull, or it can wrinkle it because there's so much force from it, from it going through there, and it's hot, so it's remelting whatever skin is there. And so, like the other case, it can wrinkle it and cause flow lines. I have pictures of the flow lines and those wrinkles in there. That's in this. Gate blush, glass appearance at the surface. If you take a heavily glass-filled material, or even not all that heavily, and you try to make it flow slowly, you'll see a lot of glass on your surface. As you make it flow really fast, one of those things about that viscosity dropping with shear rate, if you run it really fast, the shear rate goes high, the viscosity drops, and it wets out the surface, and the glass stays underneath, and you don't see the glass. So if you want to get rid of the appearance of glass, you flow the material faster so that you get a resin-rich surface, and you hide the glass. Flashing the part, flashing at the parting line. Sometimes it happens due to tool wear. Sometimes it happens, because you've exceeded the tonnage of the press. Now, for anybody who's ever drawn a free body diagram of a molding machine, I think you ought to do that for your final exam. Draw a free body diagram of your molding machine, a three-platen machine. So you have a stationary platen, a tailstock, and a moving platen. And just draw a free body diagram of how that mechanic works, and look at how long that tie bar is that's being stretched when you create the tonnage. And think about the idea FL over EA, right? I want to know how much it changes in length. When I exceed that tonnage, I'm opening it up. I'm making my part thicker. I'm giving away plastic. So I can flash my parting line by simply exceeding the limits of the four tie bars. And if it's not evenly, if that's happening at a time when the centroid of that clamp force is not in the middle, right? If my part isn't filling evenly, right, then I might have more load on one tie bar than others. So maybe I get flash in one corner, but not in others. And sometimes that's a symptom of things like cracking of the tie bars. So it gives you an indicator before you break the thing and scare everybody in the shop with the big loud boom from a tie bar breaking. Always good to detect those things first, right? Tie bar stretch, they wear, they do these things. And so the equipment that we use, we need to maintain it. We need to keep an eye on it over extended periods of time. We're not saying, you're going to buy a molding machine, you're going to break a tie bar in a month. More like, 10 years later, 15 years later, all of a sudden one day, boom, one of the tie bars broke because, people have been overdoing it. Jetting. For anybody who's ever stepped on an open tube of toothpaste or a ketchup packet, it's basically the same idea. You have a tiny little hole, and you put material through it that does not expand very much, does not have a very high viscoelastic quality to it. It doesn't respond quickly, and so and maybe it has a very low coefficient of friction, like polyoxymethylene or acetal, you might know it as, or Delrin, you might know it as. Those are POMs. Sounds like a kid's game, right? 8, 9, 10 polyoxymethylene. Anyway, so jetting occurs, right? It goes up to this pin gate and bam, it goes racing through. Shear imbalance in the runner, shear imbalance in the part. We'll see some examples of that. So short shots, right? You can see here one part's full, one part not so much. You'll also see some effects like this edge, this little sink around the edges of the part. That's a real thing. We're just starting to catch that. I don't have an image of the, and I don't have a model queued up to show you the edge effect, at least not one that I can show you. I have one in a model that's proprietary, unfortunately. But I'm starting to see this edge effect thing going on in my simulations that I'm getting out. So, you know, short shot. I got melt temperatures too low, or maybe my shot size was too small. You know, that's a simple thing out at the press. But maybe, you know, maybe I've got the wrong resin for it, or maybe I don't have the melt temperature up high enough. Or maybe I have a fill speed that's too slow. You know, I have this little tensile bar and I try to fill this thing in 8 seconds. That's a little slow. I might actually get short shots with some materials that way. So, you know, filling it faster might be more beneficial. Or maybe I have clogged vents, right? Trapped air, that can hold it back. Or simply my flow length is just too long for the resin I'm using. Flash. I love these examples like the fork here. Man, you can go to almost any fast food restaurant, pull out a fork from the pile, and you know, some percentage of the time you will see flash on those parts. Or, you know, here we see our tensile bar and we see flash on the tool. So, you know, flash could be from a worn out tool because, well, somebody was exceeding the tonnage of the press and they did it too much. Or simply that the tool was getting blown. You know, that happened early on in its life, and then you start wearing away the parting line, and then the parting line just flashes anyway, even if you do have enough tonnage on it. Another example of flash, I went out to, I think this was Lowe's. You can see around this part, all this flash around the edge of this part. And then you see all this warbling and stuff, and there, you know, there's issues, 2 other issues going on here. You know, we'll see if you can think of those before we get to the next chapter. Knit lines. Here's our knit lines, right? Here we have a nice shiny knit line. This is all texture, but yet here we have shiny. The texture isn't showing through here anymore. In fact, this can wear away your texture, having this kind of thing go on. And so what's happening is that the air traps and then the air blasts along the surface here. Whoop. Let's go back. Air will blast along it. So what happens is I got 2 flow fronts coming together, and essentially I create a capillary between the mold wall and the 2 flow fronts, and I've got air jetting through there that's being compressed upstream. And so this is putting very, very hot air through here. In fact, it can go so hot, if you look very carefully at this image, you'll see wrinkles, you know, these flow marks that are pushing in the direction that the air is blasting as this thing fills and goes. And, you know, here's our flow front out here. So when you see something like this out here, and there's our part again, here's that air trap that was causing these wrinkles as this thing blasted through. And later on, when you look at it, here it is in the final product. You can, you know, as we got a good look at it with the right lighting, you can really see the wrinkles in that surface because of that air blasting through there. They're huge. It's just a big problem. And this is a this is a console part for a car. This is something you're going to see. So this was not something that we could keep having like that. So, you know, air traps and burns cause issues like this. So you get, you know, dull spots, you get shiny spots. You see all this shine on here, and it runs all along the knit lines, right? Again, this was Lowe's. These chairs were sitting out in front, and I took this picture because it was just a perfect example of, you know, knit lines being highlighted with these shiny spots that are caused by all that air that was just not escaping until it was kind of blasting through that capillary effect. Here we see an actual burn, and so everybody, you know, traditionally people think, well, if you don't see that black thing, it must not be a burn. Wrong. These are cases where the same physics is involved. So exact same physics over here. So when you see trapped air, understand that even if you can't avoid it, maybe you have to vent through a pin underneath that area in order to get that air out. But you need to do something to take care of that air. So when we talk about splay, here's an example of splay. We got the bubbles coming through. They get bigger as they get toward the front. I should have added that in that image when I made it. Anyway, but when they get to the surface, they stretch out. And so everything stretches at the front because this is a fountain flow. Material's coming in through the middle. Material at the surface is stagnant, and so it fountain flows. And so the bubble stretches along the surface of the part, and that's what makes our splay mark. So all these splay marks you see along here are coming from a little water that was that had gotten into the hopper with this high density polyethylene, or contaminant that had gotten into the tensile bars over here. And you can just see it. I mean, this is water on this one here, and you can just kind of see how it's sort of stretched on the surface, and there's just lots of it. Gate blush. When I'm looking at a gate, this tiny little gate on this part, right into this part, this is polycarbonate. If you're looking at it carefully here, it's upside down in this image, but you'll see right here it says PC. This is polycarbonate, and the other side of this part is very shiny. And so when I'm gating directly into this part from a hot runner, and I have this very shiny surface on the other side, the shear that goes into there can essentially create a witness mark. Just like you see here, you see this, it's very shiny here, and it kind of clouds up right around it, and that's called gate blush. And really, it's a shear effect as it starts to fill and starts to form. Glass appearance at the surface. It's a perfect little part for this kind of thing. When I teach the SimLab molding class, this is the capstone project part. These tilt levers. You get glass at the surface, so you want to know that you have enough shear rate to hide the glass, right? Kind of like what you see down in here. In other regions, it's not so much. And part of the reason why it was molded slower in here was because of all the sharp corners in here. The parts would crack, and if the parts cracked, then they're no good, right? So there were mechanical issues in addition to the molding issues, and so you'd see a little bit of glass at this end, and once you got a flow front that made it around this feature here, there's a slide that comes in and cores that come from the top and bottom. Once it got around this, then you could flow really fast, and so then it would speed up. And as it sped up, especially coming into this corner, the flow front speeds up a bunch. And so then you see that resin-rich surface emerge as it gets toward the end. Another example of that, little different lighting to really highlight that glass at the surface in that part. Here's another example. This is a part out at Lowe's. You can see some of the glass kind of swirled into this part as it hit toward the end. Some of that might also be splay as well. Here it is from the gate. You can see, that high velocity coming through the gate. It shears and it wets out the surface here, and then you start seeing things like splay and glass all showing up at the surface. First it's splay, and farther out you see glass emerging in it as well. And along here you see the glass in it. You can see the fibers right near the gate as it forms. So you have kind of a mixture of splay and glass as it goes out. And that can affect the mechanical performance of a part. Now, this is a level, so as long as the thing stays straight, it should be able to do what it's supposed to do. But, that would be worrisome for me thinking about dimensional stability. Underbelt. This is not something you can predict in a simulation, but it's something that can actually happen out at the press. So if somebody comes up and shows you this part and says, my gosh, how can we predict this in a simulation? Well, you can't, because they aren't using enough back pressure at the press. And one of the things about analysis is, understanding not just what you can get from the simulation and only focusing on it, understanding what you can't get from the simulation, things that are actually manifest at the shop floor and are a defect of human error. The problem exists, between the, sort of the problem exists between the keyboard and the chair, at least along the spirit of that. So that's operator error. That's technician error, that he didn't put enough back pressure on the screw when he was plasticating, and he has unmelted pellets in his melt, And so it shows up on the surface as an unmelted pellet in the part. I hope I don't have to explain how that can affect the integrity structurally of a part. This being a tensile bar, not such a big thing. If this was an airbag housing or a seatbelt component, I'd be a little more worried. Shear imbalance in the runner. So, I've made mention of this before, right? Having a naturally balanced runner system, like you see here, but I've got 4 parts filling before the other 4 parts, right? The inside 4 filling before the outside 4. If you've never heard of the melt flipper, you can Google it, melt flipper. Or John Beaumont, Beaumont, John Beaumont. He and Dr. Hidetoshi Yokoi have probably made, Dr. Yokoi is over in Japan. I think he's recently retired about a year ago. Have made great strides in helping people understand the importance of shear thinning behavior and the effect of shear thinning behavior in feed systems and in parts. This can be a huge issue. What you see here on this was an 8-cavity mold, and they were having so much trouble trying to fill all the parts that they ended up shutting off the outside 2 just so that they get 6 parts out of their 8-cavity mold. Now, if you've never done costing for that kind of thing, that's really expensive to only get 3/4 of your production with every shot. Your overheads just jumped. So kind of expensive. I have an example of this queued up to show you. This is Dr. Yokoi's model, so you'll see that in just a minute. So here we can see in simulation, yes, we can capture this in simulation if it's modeled correctly, if you have the correct process parameters, and you've modeled correctly the geometry of the runner system and so on. So if you model it correctly, if you're attentive to the details, you have a pretty decent mesh in order to do that simulation. Yes, you can capture these seemingly subtle effects, and it's not extremely sensitive to this. Ours isn't extremely sensitive to this, but you do need to have at least a reasonable model to do that, and have it come out, match 1-for-1 with the flow pattern that happens at the press. Part of that shear imbalance in the flow, I have a sprue gate into this part, and this big 2-foot by 2-foot plaque. And one of the things you'll see is all this potato chipping that's going on, right? This is an unfilled high-density polyethylene. I'm actually going to run this at some point in the fairly near future, now that I've done some work in improving the accuracy of our warp with unfilled materials. I'm going to be testing that, and I've done it with a customer part, worked great. I'm going to test it with this because I actually have a sample to compare it against. But this potato chipping is happening because I'm getting so much shrink. I'm so far frozen around the outside edges, and I get so much shrink in the middle that this thing just, I set up this kind of anisotropy from the center outward. I set up orientation with the molecules, molecular orientation, and I have a lot of shrink just thermally going on as this goes. And so we get this warp effect. I might get more warp on one side of the part than the other, not because of cooling, but because I've gated on that side. And so I get shearing and heating that's happening because I gated right into a top surface. And so that top surface is going to shrink more than the surface underneath it, simply because of shear. And the fact that the center of flow is not going to be in the center due to that shearing. It'll be a little offset and give an advantage to the side where the gate is. Edge effect. Edge effect is, if you hear the term, it's a sink that occurs around the edges of generally thin-walled parts. Basically, what the deal is, why this happens, is that while we think of thin-walled parts as just, I can simulate them as just a 2.5D mid-plane model, and for most intents and purposes, that works, except for this, because what happens is that along the edge of the part, I have an extra shear face, right? As this material runs through here, I don't just have a shear face at the top and bottom, I got shear faces along the sides. And so I create a little extra shear heat along the sides of my part as I'm filling it, which means I'm a little extra hot out at the edge, a little extra hot out at the edge here versus what's in the middle. And so I might freeze here, I might freeze in the middle, I might freeze out here, but it takes a little longer to cool just inside of it. And now this creates a sink near the edge. And this is one where I had, recently, just last week, I had a customer part that actually exhibited this kind of behavior, and it's proprietary, so I can't show you right now. When that becomes, when they release that for use in a paper, then I'll be able to show that. Here's a couple other examples. This is jetting. Talked a little bit about this, right? Squeezing a tube of toothpaste or stepping on a ketchup packet. Basically, the material shoots all across and creates, it hits the end of the cavity or goes as far as it's going to go, and then it starts snaking back and forth until there's enough resistance to coming through that gate that it starts to form a flow front, and then it flows around it. And so in a finished part, you'll see these little swirls and things in there. Well, what happened was it came in here, it shot across here, and then it started backing up going into the gate, and then it finished filling the part. And so, jetting, that can be an issue, right? When you hit those gates, sometimes you got to slow it down a little as you go through the gate. And once that flow front starts to form, especially with materials like, this is polyoxymethylene over here, this is POM, acetal or Delrin, one of them. Over here, this is an ABS doing it. This one is a very low coefficient of friction, which is one of the reasons why it does this very, very readily. Acetal, Delrin, especially the unfilleds, but really it doesn't matter so much if it is or isn't filled, but unfilled, I suppose, a little more, even more prone to it. It will want to jet because it has such a low coefficient of friction, and it does not expand very quickly coming through a gate. If you shear it through a pin gate like this, and there's nothing on the other side to stop it from just taking off, it will just shoot across that cavity. Tiger striping. This is one that there's a few examples here that in one case here I see kind of a flat part, and it's kind of doing it as it's running out across this flat part. I see this tiger striping going on. This tends to happen in very soft materials, TPUs, TPOs, elastomers, anything with elastomer in the name, right? Something that's going to have a very low durometer, rubbery kind of feel to it. Flexible PVC is notorious for tiger striping, even in short, flat parts that don't have very long lengths and don't turn corners like you see in the other example. This is taken from a paper I was sent, where what they did was they were comparing about the speed at the outside and the speed at the inside, and found that there was some dithering that was going on in here. I'm inclined to think that that's a bit numerical in nature, especially because while I see some effect on the inside, here I see effect on the inside, not so much on the outside. Here I see effect all the way across the thing. Now, my experience on the shop floor is when people see tiger striping, the first thing that the technician does, a good mold tech does, is they go out and they clean the vents. And typically, it goes away. And if that's what's making it go away, it's not just geometry that's causing the tiger striping, it's the fact that the vents aren't clean, which means air is involved. And so if I think about another analogy, I'm going to describe this, and you can do this on your own if you like. Take a piece of copper tube and a small stack of round neodymium magnets and drop them in the copper tube, and you will see them bounce and bounce and bounce and bounce as they work their way down. And what happens is as they speed up, they create eddy current, which then resists the falling of the magnets until they stop. And then it hesitates, and because they slow down, then the eddy current dissipates, and then gravity can take over, and gravity starts dropping it down again until it develops more eddy current, and then stops the drop, and then it pauses and rinse and repeat. So when it starts to do a cycle like that, then it creates this dithering effect. So it drops and drops, it drops and stops and drops and stops. Well, if I have totally clear vents, air can get out, no problem. If I have totally closed vents, I'm going to stop the flow, period. But if I have vents that are open, just not enough, right? Somewhere in between, right? I'm not a carbon burn, and I'm not a nice clean knit line, right? I might have shiny or dull. There's something in between. Same idea. My vents aren't totally open. They're open some, but not enough. So I have this very compressible, very material. This material can compress a lot, and so as the specific volume expands, as it becomes molten, it's even more compressible with pressure, right? It's a very soft material, and so it compresses greatly. And so I'm making it flow, and then it starts to see resistance from the air pressure. It builds up pressure until it stops the flow front. What's coming in from behind still keeps coming in, but what's at the front of it, it halts the flow front and starts to compress the material behind it until the air can dissipate and get out, like the eddy current. It dissipates, and then the flow front can start picking up again until it builds up pressure and stops the flow front again. And so you get that same kind of oscillating, dithering effect. And so when you see tiger striping, it should occur to you the repetition of that is very cyclic. You have some kind of cyclic behavior going on. And typically, right, I look at this part as they show it in here, this effect isn't on one side, not the other. It's all the way across. It's the air, okay? And so I look at this as the air going into there, clean the vents, and that problem tends to go away almost 100% of the time, unless there weren't enough vents to begin with. So that's it for the slides in this. Let's look at some examples here. Let's pull up some shear imbalance. Here's a good example. So if I'm looking at this part, if you were paying attention, maybe you can, we'll have your professor pause the video or just pause it for yourself. Which cavity, if I numbered them, 1, 2, or 3, which cavity is going to fill first? Is this one going to fill first? Is that, is 1 going to fill first, 2, or 3? Give yourself a couple of seconds. 3, 2, 1. Okay, hope you made a decision. Here we go. So now we're going to make this thing flow, and I see an advantage coming here. I'm going to advance this kind of a frame at a time. And here we can see that we finish filling. This cavity is now full, and these two cavities are not, because what happens is it turns this corner, and I'm shear thinning here, and I'm actually creating a shear flow into this direction versus these two. And for a long time, many of these molding softwares were not capturing this kind of effect. It would show all 3 cavities filling at the same time, and that's just not what really happens. There are lots of other examples of this kind of thing. You can get just a simple plaque. You go to mold it out of like a polycarbonate or an ABS, and you'll see what's called race tracking effect down the edges of the part because of a fan gate that's in it, and you'll see that the flow front turns from convex to concave as it fills. And so that's a pretty significant effect when you talk about shear thinning and odd shear behaviors in a polymer melt like this. So this is really kind of an important effect to understand that it exists, and to know when you're seeing something weird that really doesn't seem to make sense, maybe this has a little bit to do with it. So this is, it's good to understand these things. Now, there are other results we can look at. See if we've got, I can also cut this thing with a, see if I got a good section here. Not that one, this one. Yeah, here we go. So when I back this up, I was talking about the shear behavior. So let's just back this up just a little bit so we can really see it on display here. So here I've got, here you can see the temperature as this thing's really going through there. And if I raise my bottom temperature and say, okay, make you, so I can really kind of see what's happening. Temperature is part of it, right? It's going this way, it's going this way, but the shear thinning is driving it this direction. So let's look at a different, result. How about effective viscosity? All right, so let's cap our top viscosity at, say, 200. Okay, too low. 1,000. 10,000. Okay. So the viscosity in the middle of this flow, right, is running pretty high in this material, right? This ABS, this Toyolac. But what happens is I'm turning this corner, I'm staying high going this way and this way, right? As it takes off. That's what's happening out here. And a little bit might track along here as it goes, but right in here, I see lots of it. And in fact, this is shear thinning a whole bunch. This viscosity is dropping tremendously in here. I'm going down to, 1 Pascal second coming in along here. I'm running down. I've got 4,000 Pascal seconds versus 10,000 plus out here, right? And so it's going to draw more flow on this, even to this side of the plaque. It will draw a little more flow coming through here. So this shear thinning effect, right? Looking at what happens to our viscosity, right? If I look at my shear rates, that's another. I go to effective strain rates, and again, I'm going to have to do some things like cap my top here and say, let's make you 500 per seconds. So, here we're looking at shear rates, right? I mean, 500 isn't all that much, but I mean, it's something, and it certainly shear thins in that region, right? And so I get thinner material as I round that corner, which draws more material in this direction, instead of following inertia going out that way. Here's a simplified model, and I'm just kind of looking at the pressure, right? The pressure goes out. And one of the things that I can see is, like, if I look at the velocity of this, I'm going to go in and I'm going to look at my velocity, and I want to look at it as I'm filling it. So here, and I want to scale this top to more like, I don't know. No, I'm going to bring that down. So one of the things we can see is a lot of flow through the center, and I can even, I don't have a clipping plane on this one. Okay. But I want to make it X. Okay, so here I can see velocities. I can kind of see what's going on here now. Okay, I'm going to make this oh, there we go. There. So we get, it's really, really fast coming in here, and then it starts slowing down as it goes out, right? And so as our flow front slows down, right, our viscosity is going to start going up out here when the flow front slows down. And so, what happens back here is, we're filling fast and we're going to be a little off center, and we're going to push out. But as this expands, right, our flow front slows down, and then that's going to start building pressure back here. And that's why we build pressure the way that we do from injection molding. So if I look at this as an animation, kind of from the top down, we'll just kind of back it up and watch it again. So you can see how it starts out really fast in here, and then it starts slowing down, slowing down, slowing down, slowing down as it gets to the edge. You can also see that it doesn't have a great deal of effect, these tiny little ribs, because really they're tiny. If they were thicker, wider, then they might have a bigger effect on that. But they were designed for the simplified model to account for a little extra volume, but not add to the length or the projected area, so that I get still the same clamp force and the same pressure to fill as I would with the genuine part that this was designed for. So I had written a compose script to create this geometry when I did this. So somewhere buried in my stuff, I have this example of creating simplified geometries for molding. Anyway, all right, so there's that one. Next, let's look at something just a tad more interesting. I'm going to peel this back just a little bit. This is from packing analysis. So I'm looking at a density plot in my packing analysis. And if I look at my clipping plane here, you'll see that my densities are quite different at the surface and quite different than at the middle versus that surface, right? And so I get, perhaps uneven shrinking happening inside this. Recall the 2 foot by 2 foot plaque that likes to warp and shrivel and do things, twist and stuff like that. Now, I created this example actually for the sake of filling, But I'm going to start with the packing analysis and kind of look at, things like the density, or maybe I look at the potential for sink marks. Right here I have edge effect on display, right out by the edge of this plaque. I have a little bit here, but right, it seems to be a little greater here, everywhere around the edge versus just inside of it. Right, same basic idea, right? I'm going to freeze really close to it, then I'm going to freeze top and bottom out here. But here I had this extra shear face as I was coming out to it and finishing filling. So I had that flow front coming out, and then it kind of hits the end. And so I have that edge effect that's happening there. These aren't really long enough to really have that, but we'll look at that in terms of the knit lines that form. You can also see some extra heating where the knit lines are forming as it comes around. Out here as well. So where those knit lines are forming, it's gonna shrink just a little bit more in those places. We might look at the temperature plot, which is not terribly interesting without having a side view of it. But there you can see the temperature as it goes. And I can pull this back and say, okay, I want to see how this happens as I'm doing it. So you start out really hot, and then it's drawing heat, and then it starts to cool. Now, if I have a mold in here, right, I'll actually be gathering heat in the mold here, and so it'll slow down this effect, the cooling right at this juncture. So as I make my model more sophisticated, instead of just having even heat transfer out of those faces, I will start to capture the collection of the heat in the tool right in those areas, and I'll become just a little more physical in my predictions. So depending on what answers I'm trying to get, right, always remembering the physics that I'm trying to capture in my simulation to get the result that I'm looking for, that's what I'm really going after. And then I can see how that cools. And similarly, I can look at my, I can look at velocity is going to be real low because all I'm doing is compensating as it shrinks and cools. I'm compensating for a little extra material to find its way into the cavity. But as I look at density, right, I can also look at that across time and say, oh, hey, look at this. I've got it, scaled a bit, and as I cool, it's, that density is working its way, and now we're getting into cooling analysis from that point. Now, if I had like a subgate in there, I would want to identify where that subgate freezes, and then use that for a basis for warp analysis, because now the mass in the cavity would be fixed. Okay. Oh, and to illustrate the filling in this case, so here, I just kind of look at it from the top and animate this one. This goes nice and quick. Now you can kind of see it slowing down as it goes. Oh, we do have a density, a proper density plot in there. Oh, it's just at the flow front. Okay, never mind. All right. But we can look at our viscosity as we go, right? Just like I was looking at before. And I can say, hey, right as this stopped, right, viscosity gets higher, right? And then it's being made to flow around that. Viscosity drops right near those corners, right? It's going to drop as it comes around the outside of this. This being rounded, it's not as dramatic. Here, it's much sharper, and so I see this band right here that's causing that viscosity to drop. And especially as I look at it through the thickness, it drops tremendously right in here, right? That's going to add to flow near that corner, right? And so, part of the idea of this model was to look at how flow fronts go around these different shapes, right? I have an oval that's aligned. I have an oval that's sideways. I have a circle, smaller circle, larger circle. I have a square, right? I have a square that's hitting the flat edge, square hitting it like it's a diamond, right? And so we can see how these knit lines form at these different sections. And one of the great things about this model is that it's doing that. The triangle, I hit the flat edge of the triangle, or I hit the point on the triangle, so that I can compare these. Maybe one day we'll build this thing. I think it would be good to compare against. Let's see, temperature, right? Same idea, right? We get our shear heating as we come through and so on. And then we can watch how that goes. Now here, this is a good place to look at air traps, right? Because, hey, look, I'm going to trap some air. So if I want to put vents in this thing, right, I had this rib on the underside. The idea of this rib was to make sure that my flow front would be nice and even going outward, that any effects that maybe came from the machine would be kind of balanced, kind of like having a buffer in a system, in an energy system, right? That you smooth out some of the inconsistencies in it, right? So it gets past this ring, and then that hopefully makes the flow front more round and even as it goes from there. And then, of course, from that, then we can see, some air trap right as you hit the other side of this, because these flow fronts are going to hit in such a way. I'm not just going to have an air trap out here. I'm going to have an air trap right up against this thing, right? But if I go to the other side, not so much. I hit this flat edge, and my knit line is going to come together real nice because they're kind of being led to each other, but I still have my air trap out at the end of the cavity. So these are places where I would want to put vents, right? And it's giving me clues and ideas about how this thing works, right? About what's going on. Now, I can also take this thing and start working it backwards and say, okay, let's see how, this really goes. Boom. And now I can really see how dramatic some of this is. This guy here is especially bad, whereas some of these others not so bad. I mean, we could get those to go, and it's not necessarily going to trap air so badly on the back side. Even this one isn't as bad as this triangle was. This triangle was really bad. Weld lines, we are going to get weld lines back there, sure. We just won't necessarily trap so much air there. And again, I can kind of draw it back a little to look at some areas. There we go. Next, we have weld lines, velocities, flow front. There's flow front temperature. Just gives me an idea of how the flow front is heating up as it goes through the cavity. I should expect to see at least a few degrees of heating up, right? If I'm coming in at, say, 500 Kelvin, okay, I'd change this to like Celsius, make it a little easier. I'm going to go to manufacturing millimeters. So I'm looking at this in Celsius. So I've got like 239, 240 Celsius going in, and I'm popping up to, I'm assuming that's what that is up there. Well, it's actually kind of green. So about 260, probably pretty close to 260. In fact, I can go up here where it says call out, and I can come up here and say, aha, there it is. And wow, this is a pressure. If I look at temperature, let's look at my, doing something to myself here. There we go, 260. So it's 260 going in. Now I don't have to have those on. So I got 260, and out near the end, right, when I was looking at my flow front temperature, well, I mean, I can kind of see it here, right? It's a little bit warmer out here, right? 260 to, 290 to 300-ish. If I go over here and I say flow front temperature, it's saying it's about 287, almost 290 at the worst, at the worst spots. Maybe not quite as much. So I'm gaining 69, about 30 degrees Celsius. It's certainly increasing. That's due to shear. And maybe I'd scale that back if that was a shear sensitive material. So there's some ideas and thoughts on that. Now, going back to our packing analysis, something I wanted to illustrate because this one has the packing analysis. There's also cooling and warpage analysis in here, but the linear warp is not going to show us much. Not in the automated way that it is today. Down the road it will, because we'll have more temperature load into it. But from the packing, there is one kind of cool thing that I do like to show, and it shows up great with things like density and temperature. I can, with like our density, where'd it go? Density. I have this little scroll thing, And I can start pulling it back and saying, oh, I just want to see things that are below whatever that value is. And so as I'm pulling back, right, I can say, okay, there's that. I can do the same thing with temperature too. I come into temperature and I say, okay, now I want to see everything that is above some certain value. So as I'm scrolling down here, I might have to come over here and tell it to invert. So I say flip mask, and now I see everything that is above whatever my threshold temperature is. So I want to see at a given time what is above. I'm going to push this thing up here to like 197, and then I'm going to pull my packing analysis backward in time. If only we could make time go backwards, right? And so now I can kind of see where all my material is that's above that threshold, this 238, or maybe I have this thing at 265. And maybe I take this thing and I say, well, it's not supposed to be a dynamic, right? So good, it's supposed to be fixed. So I'm going to take this guy and say, okay, I want to go to 200. Or I don't know if I can, yeah, I can just say 200 and hit it. And so I just clicked on it and then typed in the number. So now it only shows me that which is above 200 Celsius. So now as I animate, then I can see that, as the time goes by, I can start seeing the material disappear that is getting below that temperature. So if that was, say, my ejection temperature or my freeze temperature, right? This would give me a way to tell if a gate is frozen. I can set that temperature, I can animate, and as soon as that gate disappears, boom, I'm done. I know I'm done, right? Because then I know that gate is frozen, and that is the time at which maybe I want to export my temperatures for warp analysis. So things like that. And there we go. So it really does a lot toward the end. The time steps get a little bigger toward the end. So we got to find a way to match it up to sort of scaled timing so that we have consistently scaled timing. But you can really kind of see it disappear as it goes. One other example. Oh yeah. So now if we start getting into something like a real part, right? Here I'm looking at, as this thing fills, I can see how that, I got all these ribs and things, and now I'm starting to see some various effects, right? I'm going to have knit lines and air traps all over the place in this part, and that is going to be just loads of fun to try to mitigate and work with. And this is why I start saying things like, maybe you want to investigate putting pins in and vent from, say, some of the ejector pins in your parts. That is a viable form of venting. As long as you can get the air out, it works. And you can see where, we're cooling down, but in the intersections between the ribs, they're going to be a little hotter. If I took a thermal image of this part coming out of the tool, I'm going to see stuff like this. I'm going to see these thermal witness lines of where those ribs exist on the back side. This is what causes sink in these parts, although there's no packing analysis on this part, so I don't have a sink result for it. But you can see from the temperature result, before I ever even go for that, I can see from the temperature result where I'm going to get sinks. It's kind of obvious, right? And then, as in a packing analysis, I can look at trying to improve the density so the density variation, particularly the density variation, doesn't change greatly over short distances, because that will be the thing that causes those sink marks. Sudden changes in density. Thinking in terms of physical gradient in space. All right, so that's kind of the biggest things there. Just a few slides on the packing, although we did talk about some of this in here. So defects, common defects that are rooted into pack and hold phase. And this will be kind of fast. There's only a few slides here. Part mass variation. If you don't pack enough, if your gate freezes and you don't have even packing, right? You haven't packed out your part enough. Or if your gate's not frozen, right? This is even worse. If your gate is not frozen, you have say a very large gate, and you shut off the pressure with the gate not frozen, material is going to flow from the cavity back into the runner system, right? And so that's going to create uneven part part weights. So out at the shop floor, you're going to weigh part after part, and you're going to see large standard deviations in your part weight. That's a sign that you have not frozen your gate. If you freeze a gate too quickly and you don't have enough pressure in there, you're also going to have issues with packing. And you'll see a difference. I have some pictures in here. You'll see the differences. Sinks and voids, same basic effect. They're caused by the same principal physics. One's a sink, the other's a void. Why? Because voids occur in stiffer materials, generally amorphous materials like polycarbonate, where the skin freezes and then the inside is hot, and as it shrinks to the point where it cannot cause the sink at the surface, so it breaks away from itself in the center. It looks like a bubble, and there's no air in that bubble. Overpack. Sometimes sticking in the mold is due to overpack. If you pack these elastomeric, highly compressible materials, and you pack them too tightly, you might have trouble getting them out. Like your ejector pins just go right through the parts, even though you froze the part, but you stuck them because you might need to polish the ribs, or you need to not pack it quite so high. You can pack longer without packing higher, and often achieve the effect you're really looking for. So pack until the gate freezes. Don't necessarily pack at the highest possible pressure you can put in there. You want to have even pressure through the cavity, not necessarily the highest you can get. If you're having dimensional problems, that's a problem with the build of the mold. If you try to process it out, you will lead yourself into other problems. And whatever you get from processing in packing, you will lose it over time because of the viscoelastic nature and the creep properties of polymers. It's a losing battle in the long run. If it doesn't come out as scrap, it will come out in warranty. Warranty costs you more than scrap because it also hits your reputation. Okay, uneven density. That uneven density in a finished part can cause shrink. Excess shrink can cause warp. So there's issues with warp because of that. You can also have uneven cooling and things like that occur that cause things like that. And during packing, you definitely want to have, even though we don't refer to it as cooling, right, especially in analysis terms, but that's part of what's going on there, right? While I'm packing that part, while I'm in my hold stage at the press, I'm drawing heat out while I'm trying to just maintain even pressure. All right. Let's see. I could have excessive or insufficient cooling in inserts or lifters. That can be a problem. It creates uneven densities. If I have things like lenses, this will cause optical problems in lenses. And so I go to test a headlight or a tail light, and I get failing results of my optics. That's a problem. Narrow, deep cores that trap heat, that can be a problem. If I put really, really deep cores, they'll trap heat. They get really, really hot, and then it's really hard to get cooling out of there, and so it shrinks more on, and you have trouble dealing with your part after that, right? So getting even cooling is really hard if you're trapping heat by surrounding deep cores. Poor gate location. If you gate in thin regions, that can cause your gate to be essentially frozen up before you've managed to create even pressure in the cavity to have that happen. And so if that thing freezes off too quickly, then you can't get even pressure. And then that could cause distortions and warp and things. So part-to-part mass variation, key to stability. Packing becomes stable once that gate is frozen. Make sure that you get enough pressure in there that is fairly even. And you want, in your part designs, you want to make sure that your part designs have very even wall thickness as much as possible. If you have 2 times variation in thickness in different areas of your part, that's going to create excess shrink, warp, and cooling problems. So the more you can have the same thickness in all your nominal wall, ribs and things are going to be a little bit thinner, like 2/3 the thickness of the nominal wall. But again, you want them to be as even as possible. That's going to give you your best quality parts. Here we see a case of underpack, right? Either the pressure was cut off too soon and material flowed back into the runner system, or they shut, say, a valve gate without putting enough pressure in it. There just simply was not enough pressure in here to pack out the part, and so you see this ripple. There's a bunch of ripples in the side of this wall. It's a little hard to see here in the picture, but it's there. I mean, if you look at it, you can see kind of dark light, dark light. When I looked at the part itself, I mean, it's so obvious looking at a real part. It's just rippled on the face of the tool. Nobody would build the tool like that. That was an effect of not packing it enough. Here I got sinks, right? This is nice soft material. I got sinks in here, and you can see where every single rib is because of those, because of the sinks that are in it. And sinks are driven by the intersection between the rib and the nominal wall. And the deal is, the thicker your rib, the bigger the inscribed circle, therefore the deeper the sink. If you think of this in terms of a gradient of density, right? A density gradient in the part. As I change my position in the part, I have a density, and suddenly I get much lower density right in here. So I'm shrinking in because of this extra heat. And because it happens so quickly, it changes angles. And the angles are right? The light reflects differently off of it because of the angle change. And it's that angle change that makes you see the sink, okay? It's an optic effect. Think of all those things as optic effects because we're visually identifying the defect, right? And so it's not just how deep it is, it's how deep it happens versus how wide that feature is, right? I could sink in that same depth, but if it's way out to the far edges, I might not notice that. But if it happens very, very locally, then I'm going to see it because the angles shift. Okay, so having a smaller inscribed circle that's more like the dimension of the nominal wall means that I hopefully will not see that sink as long as I pack my part out properly because I dimensioned my part correctly. Now, sometimes you just can't avoid it. Some parts, this is a utility shelf here, right? I'm going to see sinks and utility shelves because it doesn't make sense to pack out a utility shelf any more than what's necessary for dimensional stability. As long as I'm in dimensional stability, it's not a cosmetic part. This is not a bezel in your car. This is not a console part in your car where the optics of something like that would be a detractor for selling that car, right? This is different. It's utility. People aren't worried about that, which is really great because packaging parts are great. If you want to model something and test and you want something to play against, especially as a student, go find packaging parts, injection molded packing pieces. There's lots of them around, lots of different kinds of parts, and they never, in packaging, they never try to hide their sins. You can see every knit line, every sink, everything, and they're perfect for modeling up and illustrating and trying to correlate the simulation to the defect you see that's really going on. They're fantastic examples simply because they're so cheap, nobody cared about their sins being seen. They're not trying to hide it. They don't care. It costs too much to try to hide that, and nobody cares because it's packaging. People are just going to throw it away. Single use, which of course in Europe they're trying to ban all that. So so I suppose students in Europe are going to have a harder time trying to find examples to try to model against and have something as an example to compare against. Now, we talked about sinks a minute ago. Here we don't have sinks, we have voids. Can anybody spot the void in here? Can you see the void? How about right there? Right in that little corner. Here, let's look at it closer. Right there. That's our void. Okay? So that's not air in that bubble. That's a void. It's a vacuum void. Here's another example in a different area of the part. Same thing. Another vacuum void. You can tell it's not air because where does air go? We talked about splay, right? Air in there is going to go straight to the flow front and it's going to become a silver streak on the surface because that's what air does. It goes to the point of least pressure. This is occurring in a place where you have great pressure, right? And so this is not a flow effect. This is a packing effect. Here's a much cleaner image of it. There's that little vacuum void in there. And so this is shrinking away from the geometric center or the thermal center of that geometry. That's why you're seeing that there. That's the thermal center. Another angle of the same piece, right? There it is right there, right? Vacuum voids. And one more. It's actually pretty clear there. Little, this is a little distracting, but there, nice and clear. Okay, so now let's talk about that uneven density again. Right? Here's our uneven density. Here, they packed it out enough, and yes, I can still see sinks in this, but my part is dimensionally stable, right? It's nice and straight. All the edges are nice and straight. Over here, we have a product made in another country that didn't care, wherever that shop was, they didn't really care so much about their quality. So you see flash along the edges. That was an earlier image. And you see all this warbling and stuff. You have deep sinks in this part, and the sinks in here are much deeper than the example on the right. And then the cooling and other effects are highly uneven. And so we see all kinds of warping and distortion, and there's all kinds of problems because of that. And so, some of this is process, and some of this may very well be tool design. If they didn't care about the cooling of the tool, then, then there's just no way to process that out. So, if you have any questions, feel free to email me, pfvh@altair.com, or you can send messages through the into the user community on. I think we have I don't know if we have a student user community on Altair 1. But if you've got professors who are well versed in injection molding, that's also a good source. You can look things up online. Again, professors like and speakers, people like John Bazzelli, John Beaumont, and others are out there. And attend a seminar once you get into a job position, something like that. Attend the seminar. Go out and hear some of these people talk. They're speaking from experience. They're talking about things that are going to be very germane to your job. Get into Antec, see some papers, get to talk to some of the speakers. This is a fantastic industry segment, and I see it still growing greatly well into the future. And there will always be challenges to be had in it. So thank you very much for your time, and good luck.